Okay, so hope am I audible? So let me bring out my screen, and so today we will discuss the mechanics problem and the oscillations problems. Basically, I solve few problems using RK4 method and RK2 as well. Okay, and that's help you to solve your assignment problems. So let me share my screen. So hope my screen is visible, and yeah, so so in this tutorial we will solve a few classical mechanics problems using Mathematica and focusing on driven oscillations, resonances, and we include some drag force, air resistance, okay, in the falling object problem, and also planetary escape. Okay, so we will discuss on details. Okay, so the aim of this tutorial is basically to solve 3 or 4 problems, okay, and using the method we have learned so far. Okay, so let's go one by one, and in the meantime, if you have any questions, please interrupt me, okay, and ask your questions, or you can also email to me. Okay, so all the informations are available in my web page. So so let first discuss this, the force oscillations and frictions and resonances. Okay. So basically we study the damped driven oscillator. The equations is basically second order equations, okay, where you see that this m d2 y dt2 and plus some frictions terms are there, right. So b dy dt yt, so this are linear first order derivative terms, and plus kxt, right. So without this the term that is first order in derivatives, so this is basically otherwise the simple harmonic motions, and the right hand sides there is a source. Okay, so basically force terms. Okay, so we so this is basically driven things. Okay, so driven is basically we add a force terms, okay, to keep the oscillations, because otherwise it's decay due to this friction term, okay, the first order in time. Okay, so so this is the equations for damped driven oscillator. Okay, so there is a damping term, the second term, and the right hand side are basically driven term. Okay, and we choose here cos omega t. Okay, so sinusoidal driven terms. Okay. Periodically we apply this thing. Okay, so the above equations can also be written. So if we just rewrite in terms of dimensionless variables. Okay, so so basically we divided by m, okay, and d2 dt2. So this is not exactly dimensionless variable. So we just simplifying our problems, okay, in terms of few parameters. Okay, so in this case I have a b, m, and k, and if not I have 4 parameters, right. So I just rewrite in terms of 1, 2. So gamma, omega naught, and f naught over m. So let's say we denote this parameter some another. So the parameters remains independent parameters are 4, but we just re-express in terms of in this forms. Okay, so this is standard forms. Okay, so so we just divided by m, and this is basically d2 dt2 and plus 2 gamma ddt and plus omega naught square. So this is equals to f over m cos omega t. So here we basically rewrite in this form. So this is basically to solve the problems equations easily analytically. So that's why we put 2 gamma instead of gamma. Okay, so you can also use that. So that so why where we use gamma actually b over 2m, right. So so this is for simplifications. Okay, and omega naught is basically square root of k over m. Okay, and on the right hand side is f naught over m, right. So if you solve this equation, so there is a 2 solutions. One is the transient, another is the steady state solutions, right. So transient is basically when the right hand sides are 0. That is basically your damping solutions. Okay, so die out after some times, okay, because of these damping terms. Okay, and then after some times, basically if you put a force, okay, on the right hand side, so they reach a steady state, okay, because we apply force, right. So to the system, so after some time, so there is a steady state solution. So there is a 2 solutions on transient, on the steady states, that depends on the time, right. So, the most general solutions is written in terms of in basically sum of these two, okay, transient and steady states. Okay. So, after sometimes transient goes away, but the steady state remains there. Okay. So, this is now we implement this in Mathematica. So, so basically first we assign the values of these 4 constants, right, m, b and k and f naught. So, I choose these values, let us say. So, first we clear all the variables. So, this one is basically clear all. So, whatever the variables you assigned before, so you just clear, okay, all the variables they clear, okay, global variables, okay, all the variables you clear first, okay. And then I assign 1 to m, basically m equals to 1 I choose, and k also 1, okay, and I choose b value is 0.2, let us say, okay, and f naught is f1, okay. So, I choose these values, okay, for these 4 constants, and then we calculate omega naughts, because I want to solve in these equations. So, there is omega naught. So, that is why I have calculated omega naught. So, this is basically square root of k over m. So, since both k and m are 1, so so the omega naught is also 1, and the values of gamma is basically you just calculate. So, 0.2 and m is 1. So, it is basically 0.1, right. So, once you run this, so this is the output. So, first one is the output of this omega naught. So, the values of omega naught is 1 and values of gamma is 0.1, right. So, there is one more parameter, that is omega, right. So, that is basically your driving frequency. So, this is we also put, okay. So, let us say I choose omega equals to 0.8, okay. Now, I want to solve these equations, right. So, I want to solve these equations, and you can use the numerical solver, D solver, differential equation solver. So, ND solve, okay. So, if you use ND solve to solve these equations, okay. So, basically you put the solutions, so the equations. So, this is the x double prime t, okay. So, I here use x, okay. So, you can just write in terms of y, okay, no problem. So, you just put y, and so this is y double prime t, that means the second order with respect to times, okay, because this is a functions of t, and then 2 gamma y prime t. So, 2 gamma and the first derivatives of y, and the third one is omega naught square y t, omega naught square y t, which is again there is a 2 equal signs, because this is an equations, not an assigned things, okay. So, when you put one equation sign, so that means you assign 1 to the variable m, okay. So, when you put 2 equal sign, that means so this is an equations, not an assignment, okay. Assign the values, okay, to the variables. So, this is basically an equation. So, that is why you have to put 2 equation sign, and your right hand side the term is basically f naught over m cosine omega t. So, in these equations, so you know all the values of omega, values of gamma, values of f naught, values of m, values of omega, right. So, that is why these are the black, okay. So, that means you put the values of all the constants, okay, to solve the equations, okay. Now, you have to put a initial condition. So, you define the equations here, and you put the initial conditions. So, at y at t equals to 0, so it is 0 again, right. So, this is an equations, and again y prime 0 is again 0, okay. So, you have to put 2 equal sign here, okay. So, these are the conditions, and you want to solve y as a functions of time t, right. So, that the solutions is basically a interpolating functions, okay, from t to 200, okay. And then I want to evaluate this y t with these solutions, okay, for t 0 to 200, okay, and I plot this, okay. Okay. So, this is basically, so you evaluate y t at solutions. So, this basically slash dot sol, and we plot this from t to 200, because this is a functions of t, right. Okay. So, we extract y t from these solutions, okay, at a functions of t, because this is an interpolating function. So, you just check this. So, So, this is a interpolating functions, okay, from this domain 0 to 200. Okay. So, once you put once you extract the values of this, so you just evaluate this and then plot. Okay. Right. So, this is the plot level. So, you can just a minute. So, okay, fine. So, just a minute, what is happening? Okay, all right. So, so basically, yeah. So basically, we plot this, and so this is the plot level. Okay, so you can style this. So this is basically the label and the font size. Okay, and you have to use axis level. So again, you just put this. Okay. So if you want to style your labels, axis level, so you just put the style and then the label and the font size and the color. Okay, you can also put a label, font size, color. Okay. And the tick styles are basically again the black tick, okay, the minor and major ticks, and with the size. Okay. And axis styles are basically again black and thick. Okay. So basically these are the axis lines. Okay. So once you plot this, so you see, so this is the solutions from 0 to 200 in time. Okay. And you see it is not falling. Okay. So it is basically after sometimes it's steady states. Okay. So if you closely look into after 100 t, okay, so you see the amplitude is almost constant. Okay. So that means so initially they increase and then fall and then again go back to your steady state. Okay. So damping thing is there, but after some times it is steady states. Okay. So if you closely look into 150 to 200, okay, so you can see. Okay. So you see the steady state. So amplitude is almost constant. Okay. So that means the system reached the steady state solutions. Okay. After around, let's say, 150. Okay. So yeah, so this is the displacement, and this is the plot. So now you can also calculate the amplitude and see the resonances. Okay. So if you calculate amplitude, so first I clear omega. So this is here I choose omega equals to 0.8. Now I have to clear this. So because I have to calculate for various values of omega, right, and see for which values of omega there is the highest amplitudes. Okay. So is there any resonance behavior in the systems? So let's see. So first I clear this omega. So that means my omega is if any number assigned to these omega variables, so is already clear. Okay. So you see that the omega is now in blue. Okay. So that means there is no values in the omega. Okay. So you can just quickly check. So if you just put an omega and then put, so there is no numbers, okay, assigned to these variables. Okay. All right. So so now I sorry. Yeah. So now I basically now I calculate the amplitude. So amplitude as a functions of omega. So so basically I consider again these equations. Okay. So x double prime t x t, and where my omega is basically now a variables, right. So that is as a functions of. Okay. So I calculate amplitude for as a functions of omega, right. And this is the solutions. Okay. And with the initial conditions again x 0 0 and x prime 0 as before, and x is goes from 0 to 200. So sorry, t is goes for 0 to 200, and I solve x. Okay. So okay, better to solve put a y, right. So I just initially wrote x, but yeah, so this is an equation of y, so we just wrote y, okay, instead of x. Yeah. Okay, so because your equation is basically a function of y, so but this is dummy variable, so you can just change to any variables, that's not a problem. And once you solve this, so this solutions is again is an interpolating functions, right. So in order to extract this, so your steady state solutions, so here I assign to steady variable, so I assign this number to steady variable because I want to extract the steady state solutions, right. So that's why my time interval actually in a high range of t. Okay, so let's say if you see from this, so your steady states is let's say around 150 to 200. Okay, so that's why I choose t values 150 to 200 with a step of 0.1, right. So I want to calculate the amplitude of these oscillations in this range, right, 150 to 200. Okay, because in this case the amplitude is almost constant. Okay, so I choose the better regions where actually I know that steady state is occur. Okay, so that's right for different values of omega, right. So I do not know what is the values of omega, but you naively expect that that at this values of t, so you reach steady states. Okay, so that's why I choose this range, and I assign my y values. Okay, so basically the values of the amplitudes to this steady variable. Okay, so this is only for steady state oscillations, and now I calculate the maximum values of this. Okay, so at given t value, so this is basically you calculate this the y values. Okay, so this is basically you calculate the y values at the given t values. Okay, so t values is basically least, right. So you least 150 to 200 with a step of 0.1, right. So let's say 150, 150.1, 150.2, 150.3. In this way, you can you calculate at all points. Okay, you calculate the values of this. Okay, values of y. Okay, basically amplitude. So and then you calculate the maximum values of the absolute values of amplitudes, right. So why you think, because there is a positive and negative. So I calculate absolute values of this. Okay, because I want interest the maximum the magnitudes. Okay, not the direction. So it can be both in positive or negative directions. Maximums can reach both positive and negative directions. So I want to calculate the amplitudes in so that's why I put an absolute values of this, and then I calculate maximum values of this study of this amplitude. So right. So for a given omega, right. So you calculate what is the maximum amplitudes, right. So is this clear? So basically you calculate the this steady or the amplitude values for all the t values, right. So in this range. So this is basically the symbol is basically map to. So you calculate the amplitudes for all t values, right. So t values is a list. Okay, and that run from 150 to 200. Okay, in a step of 0.1, right. So you calculate at every time step. Okay, you calculate y. Okay, and then you calculate the maximum values of from this list. Okay, what is the maximum values of? So that is basically gives you only one number, right. So amplitude that actually gives you only one number, okay, for a given omega. All right. Okay, now I run this. Okay. So you can calculate this. Okay, we will check. Okay. So this actually gives the numerical values of the solutions at time t values. So this is basically map to. Okay. So you calculate the values of your of the solutions at time t values. So t values is a list. Okay. And you calculate every time stamp. Okay, what is the amplitude? So and now we calculate maximum values of this. So maximum absolute values of this amplitude, because amplitude can be positive or negative, right. So I calculate the absolute values first, and then I calculate the maximum values of this amplitude from this list. Okay. and yeah, so we if we solve these equations analytically, right, so the solutions in this form. So x t equals to a omega, so amplitude times cos omega t minus delta. So delta is a phase and this omega is your driving frequency, and amplitude is also depends on driving frequency. Okay. So for each driving frequency omega, okay, your a omega is the maximum steady state displacement, right. Okay. So for a given driving frequency omega, so this is your amplitudes, okay, and that gives you maximum steady state displacement, because reach some maximum steady state displacement. So if the formula of a omega is basically f naught over m square root of omega naught minus omega square and plus 2 gamma omega and whole square, right. So you see at some values of omega, because you know what is your values of omega naught, that is the natural frequency, okay, that is already you calculate here, right, given the values of k and m, what is the omega naught. So my omega naught is 1, right. So now you see at some values of omega this amplitude become maximum, right, because at some values of omega the numerators is basically minimum, okay, right, because the denominator, if the denominator is minimum, that means the amplitude is a maximum, right. So if you vary omega, okay, around omega naught at some point of omega values, okay, the amplitude is maximum, okay, and we will see. So basically we construct a table, okay, the omega versus the amplitude. So I vary omega 0.2 to 2, right. So my natural frequency at 0.1, sorry, my natural frequency at 1, right, omega equals to 1. So I vary omega 0.2 to 2, okay, with a step of very small step 0.05 step, okay, so that I can properly see that if there is any resonance curve or not, okay. So you create very small steps, okay, and calculate the amplitude for each values of omega. So this is basically we create a table for that, okay. So once we create a table, so this is my table, okay, and you see that from 0.2, 0.25, so at every values of omega you calculate the amplitude, the maximum values of amplitudes, right. So this a omega is basically maximum values of amplitudes, okay, and you calculate this, okay. So they actually, so this actually calculate the maximum values of amplitudes, okay. So they return the maximum values of amplitudes in the high t region, okay, where you know the steady states achieved, okay. So you can also check by plotting this these equations for a given values of omega, okay, and you can almost expect that at a high t in the range at least 150 to 200 the steady states must be occur, okay. Yeah, so so now I plot this. So this is my again a data set. So you have to plot list plot, okay, and so list plot basically only plot the dot points, okay. So if you connect the lines, so you have to use list line plot, okay. So so in this case I just plot list plot, and this table I plotted here with x versus y. So in x axis my omega and y axis is the amplitude. So I label my x axis to omega, okay, and this is again front size, and this is the color, and y axis I label with amplitude, okay, and the front size again 18 and the color red, okay, and the plot level at the resonance curve. So if you see, so you see there at omega equals to you see at omega is nearly 1, okay. So around 1 you see there is a resonance. So that means amplitude suddenly high and then fall, okay. So this is a resonance, right. So so you vary omega, okay, from 0.2 to 2, and you see once you close to omega naught, right. So here omega naught is basically 1. So you see there is a resonance. right. So, the numerical steady state oscillations amplitudes of a ramp driven harmonic oscillators as a functions of omega, right. We see that how the amplitudes changes as a functions of omega in the steady state solutions. Okay. Because I only observe late time behavior. Okay. At omega close to omega naught, we observe that there is a resonance. So, and that should expect, right. So, you can check, but the actual frequency is not omega naught, right. So, the actual resonance frequency, if you calculate analytically the resonance frequency, because you just maximize this thing. So, you maximize a omega. So, that means you minimize this. Okay. So, you know that how to minimize this. Okay. So, you just calculate the derivative of these, and then you calculate at what values of omega. So, this gives the minimum value, right. So, so this basically if you calculate this omega r is basically this, okay, omega naught square minus 2 gamma square, right. So, this is the actual resonance frequency, square root of this. But so why you observe that your omega actually very close to 1, because of gamma, right. So, if gamma is very small, right, so then omega naught is very close to omega r, right. So, that means your resonance frequency, this omega, okay, is very close to, here you see your omega is very close to 1, right, because you choose gamma to be very small, 0.1, right. So, here you see that the values of gamma is 0.1, right. So, if you calculate gamma square, so this is again very small, right, 0.01, right, and again 2. So, basically you just subtract very small number to omega naught, okay, that is almost omega naught, right. So, that is why you see your resonance frequency is basically close to omega naught, right, but that is actually not. So, you can easily observe. So, so you just change let us say b to 1 again, okay. I just put that all the values are 1, right. Now, my gamma is basically half, okay. So, that means 0.5, okay. Let us see. So, at these values of this, I choose again omega my 0.8, okay, and then if you again see that check that, okay, is this region safe for the steady states, you will see that 150 to 200 almost constant, right. So, I calculate the amplitude in this region, that is perfectly fine, okay, for the steady states things, okay. So, then I calculate this, and then I calculate the resonance table, and then I plot this, okay. So, you see here. So, here the peak is the high peak is not 1, right. So, you will see, right. So, this is not 1, right, it is shifted towards left, right, not right, because you see that omega r is always less than omega naught, because gamma is greater than 0, right, and also there is a gamma square, right. So, if gamma is basically greater than 0, so and the omega r is always less than omega naught, okay. So, you also already observed here, right. So, you see here the omega r, the resonance frequency is not 1, right, but in the previous case you see that this is very close to 1, but in this case, and also the broaden the resonance peak. So, in the previous case, so if you just see, so in this case, so you see that this very sharp resonance, right. So, once you increase the gamma, okay, or the damping factor, if you increase this, okay, so you see that the resonance width are basically broader, okay. So, that is the main difference, okay. So, once you increase this, okay. So, this means the damping shift the resonance peak to the lower frequency, okay. That is the slow response, right. So, once we increase the values of gamma, basically you are basically damping the systems, okay, slowing the systems to response this, okay. Right. That is the physics reasons for that, okay. That why we increasing the gamma Yeah, so and we observe that, so after infinity the gamma we observe that the resonance peak is basically to a lower frequency. So that is the reason. So and you can also manipulate these things. The better way we can basically manipulate the omega, okay, to different values of, sorry, manipulate the gamma, okay, to see the how this is changes, right. So you can also do that in Mathematica. So you I mean we also discussed this is before, this functions manipulate. So in this case you just define the module, but here the two functions, one is the amplitude and is the omega r. So this is the resonance frequency, so this is the omega r. Okay, so you calculate omega r, this is basically omega naught square minus 2 gamma squares, because this is square root. So provided that this will be 0, okay, otherwise this is 0. So what these functions gives here. So if omega naught square minus 2 gamma square is greater than 0, then they return this, otherwise they return 0. Okay, that is the functions if. Okay, actually do. So you can check first. Let's say so they can check, yeah. So here, so if you see, let's say I have a variable x, right, and if x greater than 0, they return positive. Okay, otherwise they will return negative or 0, right. So there is a 2 commas. Okay, so one is, this is basically so the structure is basically if we have some condition, right, and if this condition is true, then they return true part, and if you put if the condition is false, they return false part. Okay. So the structure is basically conditions comma true part. If this condition true, then they return true part, this part. If this condition is false, they return this part. Okay. So you can check by just by this simple example. So this is basically, let's say I have a variable x. So if x greater than 0, they return positive, otherwise they return negative or 0, right. So I assign this to a variable z. So now I calculate z, let's say at x equals to minus 1, right. So that is the way we can calculate. So z slash dot x goes to minus 1, right. So at values of x equals to minus 1, I calculate z, right. So that means if so z is now my conditional expression. So what should it return? So it's return this one, because x is not greater than 0, right. So this is a false statement. So they return false part, right. So negative or 0, right. So you see this is negative or 0. Let's say I gave that x goes to 1, right. Okay. So if we put x goes to 1 and calculate the z, so this is again a conditional expressions, right. So they, and you see that once you assign to the value 1 to x, so this is basically the condition is basically true, right. So they return true part. Okay, right. So it will return positive, right. So you see it will return positive. Okay. Hope it's clear now, right. So so this is the functions used here if. Okay. So basically if this is negative, then this is imaginary. So I just put 0. Okay, if this is imaginary. Okay, sorry, if this is less than 0, so then we cannot calculate the square root, because the square root gives you the imaginary number, right. So that is why if this is false, they return 0. Okay, such that there is no issue with the calculations. Okay. And then you calculate the amplitude. Okay, again you calculate the amplitude using the same form. Okay, same way. So you just calculate this. So this is basically okay, I have calculated the amplitudes just by putting this formula. Okay, analytical formula. You can also calculate by solving these equations, and then you calculate the maximum values of this, but I use here this formula. Okay. And I plot this a omega, amplitude omega, okay, and from 0 to 2 omega naught. Okay. So this omega naught is basically natural frequency. So I plot from 0 to 2 times my natural frequency. Okay. So here I choose natural frequency 1. So I have to plot 0 to 2. Okay, for omega values of 0 to 2, and again I choose plot range all, such that they can cover all the values of y axis in the plot. Okay, and then plot styles is basically I choose thick such that the line width is somehow large to make visible. Okay, and then I choose axis level. So, this is style and then so this is x axis. Okay, so I put omega x axis level with a red color, and this is again y axis level a omega with a red color, and this is plot level. Okay, resonance curve, and this is omega r, because omega r is basically vary. So, 3 to 2. Okay, and so you calculate omega r using these expressions. So, once you know gamma, okay, so you calculate omega r, right. So, from this expression, so you can calculate omega r, okay, the values of omega r, okay, and yeah. So, and yes, so now I calculate. So now I put epilogue. So what is epilogue? So epilogue is basically you just add a extra object to the main plot. Okay, so epilogue is an object, additional graphical object. So we draw extra graphics, okay, on the main plot. Okay, so that's why we use epilogue. So this is my main plot, but I just put a epilogue. So this is basically line. So first I add a blue line, okay, and blue dashed line, okay, from omega naught to 0 to omega naught to 5. So this is basically at omega naught at natural frequency I draw a blue line, okay, from 0 to 5. So this is y axis. So I can draw a line from y equals to 0 to y equals to 5, okay, at omega naught, okay. So at natural frequency, that is blue dashed line, and I also draw a red line, okay, at omega r, okay, at resonance frequency omega r, okay, and again from 0 to 5, okay. So the y values of 0 to 5, okay. And I vary so gamma from 0 to 1 with the step of 0.1, okay. So I vary gamma 0 to 1 with the step of 0.1, okay. So you once you do that, so you see the panel, okay. So you see the panel. So first so this is the values of gamma is basically 0.05. So first check that at 0.1, sorry, gamma is, yeah, so 0.1, right, yeah. So at gamma, let's say this is 0.1, okay, you see. So as you already see before, right. So this is the type of resonance, and where this omega is very close to omega naught, right, but this is not exactly omega naught, right. So if you again going to smaller and smaller values of gamma, so it's almost overlap, okay, and it also amplitude is large, right, because I plot this epilogue, okay, from 0 to 5 in the y value. So that's why they only go up to 5, okay, all right. So and yeah, so now if we going to smaller and smaller, they almost overlap, okay, see. So there is a no blue curve, okay, almost overlap with this. So just closely increasing and slowly increasing the values of gamma. So basically the deviating the omega r and omega naught. So you see, but the omega r, the red one, okay, so red one is the omega r. So omega is always less than omega naught, okay. So you can see. So we are just increasing slowly the values of gamma, okay, you see. Right, and also the resonance width are broader and broader, okay, once you increase the gamma. Okay. Right, at some point there is a no resonance, so only temporal. Okay, so this is the reason the manipulate can helps you to visualize such things, okay, in Mathematica. So the blue dashed line again the resonance frequency, the natural frequency, sorry, the natural frequency, and the red line are the resonance frequency omega r, okay, and the steady state things are basically. So you can also write the steady state solutions, okay, using this complex form, where the xt is basically the real values of this f naught over m, and then so this is basically imaginary number. So, you calculate the real values of that, and this is also real number, right? Sorry, imaginary number e to the power I omega t. Right? We can also express in terms of cosine and sine, where the phase shift delta is basically argument of this number, okay, of this expressions. Okay, so omega naught square minus omega square plus 2 gamma, sorry 2 gamma omega. So, you can calculate. So, so this is basically also you can calculate tan delta. So, since this is let us say z plus sorry z equals to x plus iy. So, this is in complex number, right, and if you calculate the argument. So, this is basically your phase shift delta. So, the tan delta is basically y over x, right. So, in the complex number you can calculate this for any complex number. So, tan delta is basically this, and that is basically 2 gamma omega over this, okay, omega naught square minus omega square, right. Yeah. So, so you see that the phase actually smoothly grow from 0 to pi, right. So, and at pi by 2, so there is a resonance, and you can also calculate the absorbed power. So, the power absorbed is basically P average. So, this is basically proportional to this, okay. So, 2 omega gamma square and divided over omega naught square minus omega square and then square plus this. So, this is the analytical formula, and this is the proportionality constant f naught square over m, okay. So, and the maximum power occurs again and near resonance, where the phase basically pi by 2, okay, and near resonance, okay. And this is basically the phase actually go from 0 to pi, okay. So, now we can also plot all these things like the phase shift and the absorbed power, right, and we see that how this changes with the resonance, okay, with the frequency, okay. So, with omega, right. So, now I here manipulate all these things. So, one is the amplitudes and the phase shift and the power, okay, absorbed power, okay, P average. So, again I module these things, my A, amplitude, phase, power, and this is omega r, right. These are the variables. So, I calculate amplitudes again from this formula. So, I discussed before, and the phase is basically the argument of this number, okay. So, you just put a I, capital I, this is basically lead to this imaginary number I square root of minus 1. So, in Mathematica already embedded this. So, you just call capital I, okay. And that actually lead to this, okay, delta, okay. This is my phase, okay. This is also functions of omega, because all the values of gamma and omega are basically gamma is a manipulator, okay. So, is a manipulator, okay, and omega is basically functions of this, okay. And we calculate omega r, okay, again the same things, okay, as we did before, and then we calculate the power. So, power is the formula is this. So, you just plug these values here, expressions here, right. So, f naught square over m and then 2 gamma omega square and then divided over this, okay. So, now I basically plot all these things in a grid, right. So, you call a grid, okay. Within this grid you have to plot 3 things, okay. So, one is first plot a omega versus this. So, this is again this. So, where I put a epilogue, okay, the resonance frequency, right. So, you know what is epilogue here, right. So, epilogue is basically draw an additional graphics on the main plot, okay. So, this is the epilogues. I draw a line at omega r, and the second plot in the grid is basically phase, okay, where I also draw a epilogue, okay, at 0 to pi by 2 to 2 omega naught to pi by 2, right. So, basically, so this is so at pi by 2, okay. So, at delta equals to pi by 2, I draw a line, okay, from 0 to 2 omega naught, okay, is parallel to x axis, okay. And I also plot a power, okay, in the third element in the grid. So, I also plot a power, okay. and I put there is no epilogue here. So, I just plot only power. Okay. So, if you see, and where I vary, and gamma is basically 0.01 to 0.8 in a step of 0.01. Okay. And so, this is basically my initial values. Okay. So, they start at 0.1, now you have to vary. Okay. So, this is basically this. So, gamma comma 0.1. So, that means they calculated 0.1 and show you the results at 0.1. Okay. And this is the manipulator. Okay. Okay. So, from 0.1 to 0.8 is a slider, okay, with a step of 0.01. Okay. So, this is the all things in the manipulate functions, you know, right, and this is the result. So, you can just increase this. Yes. So, you can see the first one is the amplitude, so as is before. So, at omega gamma equals to 0.1, right. So, this is very standard example that I already discussed above. Okay. And you see that at resonance omega equals to 1, very close to 1, you see the your phase is basically pi by 2, right. So, this is dashed line is basically pi by 2 line, right. So, delta is pi by 2 1.57. Okay. And you see at omega equals to omega naught is very close to 1. So, so this the phase is basically pi by 2. Okay. And also the power is maximum, okay, at omega close to omega naught. Okay. So, now if you change gamma, so if you change gamma to, let us say 0.2, okay, you see the omega are shifted from 1, okay, that is already observed before, and also your phase is basically changes phase things, but you see that in this case omega not sorry, I mean phase is not pi by 2 at omega equals to omega naught, right. So, this only occurs when gamma is small. Okay. The phase is pi by 2 at resonance only occur when natural frequency is very close to your resonance frequency. Okay. And the power is also things like that. So, the way they are changes. Okay. So, if you just increase more and more, okay, you see this kind of things. So, at natural frequency omega equals to omega naught, the power is maximum. Okay. See. Okay. So, this is but your amplitude is basically maximum at resonance, and that shifted towards left. Okay. Okay, so now I solved this problem using RK2 and RK4 method. Okay. So, this maximum power occurs near resonance when and also your delta is pi by 2 when gamma is small, right, damping is small. If you increase the damping, okay, so then this is not occur. So, you have already see, right. So, so plot this, so you can check these expressions. Okay. So, I think this expression is correct. So, you can also check with the you can also check and try it yourselves. Okay. Okay, so yeah, so now I am going to discuss the different oscillations using RK2 and RK4, right. So, basically I solved the same equations as before, but using these two methods, okay, RK2 and RK4. So, again so this is a second order equation. So, I just convert this into two first order equations, right. Okay. So, this is second order. So, I just convert this into two first orders, that is the first technique, okay, and put in a matrix form. So, ddt of x v, so this is basically first one v, and the dv dt is basically now my 2 gamma v minus and minus omega naught square x plus f naught over m cos omega t. Okay. Okay. So, now I assign omega is 0.8 and my functions are basically a matrix form. So, I also so this is my functions, let us say f of x v. So, f of x v, okay, is a matrix, and I fund yeah, and df dt is basically this. Okay. So, whole matrix. Okay. So, the first element is v and the second one is minus 2 gamma v and this. Okay. So, put a initial condition. So, this is basically first one is x and the second one is v, right. So, the initial values of x and the initial values of v. So, both are 0, all right, and yeah. So, then you basically construct a functions RK2, okay. So, this is generalized functions for works for any values of any format of f, okay, and y naught, and this is basically t naught to t max, and this is the time step h, okay, and yeah. So, that we also discussed this in the previous class. So, just quick reminder. So, this is the module again we create. So, t list is from t naught to t max with a gap h, and then we calculate in step and y list. So, and the first element I assign to y naught, and the remaining one I calculate using this loop, okay. And ultimately we calculate the t list and y list, okay, and then we format in a table, okay. So, that's why it transpose this, okay. So, all these things I discussed in the previous classes, and yeah. So, now I call these functions, okay, to solve these equations, okay. So, this is f, and so first f and then x naught, and I solve from 0 to 200 with a step of sorry, h is 0.5, and now we extract only the amplitude y RK2. So, you can extract this. So, the first one, and this is the time, and this is the basically your amplitudes, right, x, okay. So, this is basically x and v. So, first one is t and then x, okay. So, that is why we extract one, and then there is again array, okay, because this is an array. So, you have to extract the first element of this. So, you extract the first element of 2, okay. So, now you plot this. So, you see this is almost things like that, because your omega naught are basically, yeah, this one, right. So, I choose this value. So, I already defined this. Okay. So, that is why my solutions is basically same to the exact one, okay, almost. Okay, now you can also solve this using RK4. So, you can again construct RK4 module. So, this is basically same as before, but here now we have 4 updates, okay. So, this is basically midpoint update, but here, so you have to update 2 at midpoint and then update at the final step, okay, h. So, this is the RK4. So, basically we have a 4 update, okay. And so yeah. So, this is basically now I again the same way we call f, okay, and solutions is now stored to solutions RK4, and I extract y from this the same way, okay, and y and t, right. So, this is the values of t and this is the values of y, okay. And now I plot this, okay. So, list line plot is basically I connected the dots, okay. Yeah. So, you see again the same, okay. But you can also calculate the error, okay, within RK2 and RK4. You see that the RK4 is better than RK2, okay. So, these things are discussed in details in the previous classes. Okay, all right. So, now I will solve a few examples, okay. So, yeah, so now I use only RK4, okay, and to solve some problems. So, these are the problems are very close to your assignment problems. Okay. So, the first one is a vertical falling object with quadric drag force, right. So, you consider a body of mass m falling under gravity g with a drag force. This is basically quadric to v to the yeah. So, quadric to v to the v. Okay. So, it is basically v to the power 4 proportional to, right, and with a minus sign, sorry, because this is drag force, okay, and kind of resistance, okay, air resistance. Okay. And the equations of motions is basically so m d2y dt2 and with equals to mg. So, this is basically for free falling, and now we have add a quadric drag force. So, it is basically minus k dy dt whole to the power 4, right. So, let us first put these equations into a dimension less form. Okay. So, we define a dimensionless variables tau. Okay. So, this is my time, let us say, and chi, this is a distance. Okay. So, using the scales, that is basically my tau is basically t over t c. So, where t c is basically m over k g cube to the power 1 over 4, right. So, you can just quickly check that this is also a dimensions of time. Okay. And the distance scale is basically y c. So, square root of m by k, right. So, yeah, so now I basically define tau. So, this is basically t over t c. So now my tau is basically dimensionless, okay, dimensionless time, and chi is the dimensionless displacement, okay. And the dimensionless OD is basically in terms of chi and tau. So, this is my equations, okay. So, d 2 chi and d tau 2 equals to 1 minus d chi d tau to the power 4, right. And we split the second order OD into a first order ODs as before, okay. So, basically system of first order ODs, okay, and we solve these equations, okay. This is dimensionless form, okay, where there is a no constants, okay, right, because all the constants are basically I replace in terms of dimensionless variables. So, basically define a time scale and length scale, and then you just construct a dimensionless OD. Okay. And now we split this second order equation into two first order equation, and this is this, okay. And this is, now we can also put this into this matrix form, okay. And yeah, so we can assign the functions f, okay, where the chi and v. So, the first one is v and the second one is 1 minus v to the power 4, okay. So, if you write in this in the matrix form similar like this, okay. So, yes, so now I have, so basically I define a functions, okay, for this two ODs, okay, into a matrix form, okay. And yeah, now I want to solve this with n max equals to 200 and tau max at 1, right. So, basically I calculate the distance, okay, the dimensionless distance, okay, chi at tau equals to 1 with a n max 200, okay. This is my problem, and using RK4 method, okay. So, I use n max 200 and tau max 1. From this I first calculate h, right, because n max is provided in the problem, right. So, and you know at what point you calculate your distance, right, at what time, right. So, that is basically tau max, okay, dimensionless times. So, at tau equals to 1, if you calculate tau equals to 1, so that means your tau max is 1, and you calculate h from is basically tau max over n max, okay, right. Since you have to use 200 step, okay, that is basically n max is total number of steps, and you have to reach 0 to 1. So, that means your h is basically tau max over n max, okay. And this is basically the numerical values of this, and you see that h is basically 0.005, right. So, if we change n max and tau max, you have to calculate age again for these specific values of n max and tau max. Okay. So that's why you cannot choose age randomly. Okay, if there is a given if the n max or tau max is given in the problem. Okay. So you first calculate the age, and then we solve these equations using RK4. We define RK4 previously. So you just call this, and again this is the functions f, and x naught is again I already defined here, right. So this is my initial conditions again. So if you change the initial conditions, then you can define the initial, what is your initial conditions. Okay, but I choose the initial conditions same. Sorry, I choose the initial conditions same at is, so x0. Sorry, so basically x. Yes, so basically x naught. So my values of x, chi, and values of v are both 0. Okay, at t equals to 0, tau equals to 0. So yeah, so now you can also define the initial values. Okay, then you can calculate solve this. Okay, and using this RK4 module. Okay, and yeah, and the h is already calculated here. So you just run this, and then you extract the values of chi, again the first one, right, because this is gives you the values of tau. Okay, and the values of chi stored in the first component of the second array. Okay, so that's a 2, 1, and then you extract the values of chi at tau equals to 1. So tau equals to 1 is the maximum. So you extract the last element in the array, right, and the second one, because first one is the tau. Okay, and the second one is the values of chi. Okay, so if you extract the values of chi at tau equals to 1, so that means you extract the last the values of chi at the last element in the array. Okay, so this is this. Okay. So chi at tau equals to 1, 0.473 to 44. So if you do not put -2, so this is basically return both the values of tau, and so the first one is tau and the second one is the chi, right. So 1 comma this one. Now I extract only the second one because this is the chi values. So you just put comma 2. Okay, sorry, this is comma 2. Yeah, this, right. So this is the dimensionless distance at time tau equals to 1. So now you can easily change the values of n max or tau max, okay, according to your problems, and you calculate the distance at that time. You can also plot this. Okay, so you can also plot this chi at 4 RK4, okay, as a functions of chi t. Okay, so this is the plot. Okay. See at tau equals to 1, your chi t is basically 0.47 around, and is basically almost rapidly increasing because your your drag force is basically quadric. Okay, sorry, quadric drag force. Okay, okay, so okay, now we can also solve this using more elaborate way. So let us say for n max equals to, let us say 300, I calculate this. Okay, so you can calculate for n max equals to 300 and t max 1, and then you calculate h. Okay, and this is the initial values, tau equals to 0, chi equals to 0, and v equals to 0, and then I create a data set. Okay, empty data set. Now I basically append the values of tau, chi and v to this data set, okay, and using these procedures. Okay. So, this is my RK4 steps. So, my first one is basically v 1 minus v to the power 4, then I update at midpoint, okay. So, k2 and k2v, and then I again update at midpoint, okay, 2 times I update at midpoints, okay, and then I update the values at endpoints, okay, and at the end I calculate this. Okay. So, this is all the RK4 methods actually, and your tau is updated basically tau plus h, okay, and you perform the loop, okay, up to n max, right, and at the end the values of chi actually the values of chi at t max, okay, 1, right. So, basically so one should do that, right. So, what is the values of chi, right, because if you call the values of chi, that they return actually the last values of chi, okay, that means the values of chi at n max, okay, because you perform the loop, okay, n max times, okay, in a step of h, okay, h is calculated this, right, from the t max. Okay. So, that is why, so you just calculate the chi final, actually the values of chi, okay, last stored in the loop, the last values, okay, stored in the into the variable chi. So, that is basically this, okay, 0.473244, okay. So, exactly same, okay, as you calculate before, okay. So, you can also define a RK4 module before, but you can also do this by explicit loop, okay. Okay, so you can also plot this, okay, the same thing, okay, you just plot data all, and the 1 comma 2, the first one is your tau, and the second one is the displacement. So, this is basically your chi t. Okay. So, yeah, and this is basically the way you can basically, so this is the different way I solve the same problems. Okay, and yeah, I think okay, fine. Now I now I solve another problem. I don't know why I wrote those things, but yeah. Okay. Now, I solve another problem. So, basically a harmonic oscillator subjected to an external force, right. So, this is a non-dimensionalized differential equations, basically dimensionless form. Okay. So, you see that d2x dt2 plus x. So, there is a no variables. Okay. So, here t is the dimensionless time, x is the dimensionless displacement. Okay. And so, this is basically your dimensionless what is, and again t is the dimensionless time, and this is basically proportional to, so t cube. Okay. So, your driving force is proportional to t cube. Okay. And you solve this. Okay. So, again we can split these equations into two first order equations, right. The first one is basically dx dt equals to v. So, I just assign x1 and x2. So, x1 is basically my x, and x2 equals to basically v, okay, dx dt. Okay. And so, the first functions is basically x2, and the second functions is basically minus x1 plus t cube. Okay. So, I do this in different way, because you can also do in this way. So, you can also define a functions into this matrix form, but here I split this into an f1 and f2. Okay. So, just I solve the problems into a various way, okay, in this tutorial. So, every aspects of things you should understand. So, that is the aim of this tutorial. So, so I assign two functions f1 and f2 for because of these two equations, two ODEs, okay, first order ODEs, and then my t naught is 0. So, initial time and the t max 5. Okay. So, I calculate the displacement at t equals to 5. So, that is why I put t max 5 and my n max is 300. Okay. So, that is given in the problem, and first you calculate h, okay, from this. Okay. So, how to calculate h? So, h is basically the numerical values of t max minus t naught. So, here t naught is 0, but we just use this variable t max minus t naught over n max, okay. And your t is basically t naught and so initial value, and x 1 is basically 0 at t naught. So, at initial values of x and initial values of v, okay, x 2. Okay. Now, we perform the loop. So, here because of two functions f 1 and f 2. So, basically we see that the first one is initial update, okay, and then I update at midpoint, and then I update again at midpoint. Okay. Okay, just a minute. Okay, so I again update at midpoint, and then I update at end point, and then I calculate x 1. Okay, so this is basically x 1 plus, so this is weighted average, okay, and then x 2, okay, similarly, and I calculate update t is basically t plus h and up to. So, we perform the loop up to n max, okay, with a step of h. Okay. So, at the end your t equals to basically 5, because your n max is 300, and you calculate h accordingly. Okay. So, that is why. So, basically once you do this, now I calculate x 1, the displacement at t equals to 5. So, you just extract the last values of x 1, okay, from this loop. Okay. So, you just extract the last values, okay, from this x 1 thing. So, you just see that so this is the values of x 1 at t equals to 5, okay, right. So, you can also solve using the previous methods. Okay. So, you basically put in a matrix from, and then define a functions. So, here the functions is basically x 1 x 2, the first one is x 2, and the second functions is minus x 1 plus t cube. So, yeah, so this is my second functions minus x 1 plus t cube, okay, and I define the functions, and this is my initial conditions, okay, 0 0, because I also use here the initial conditions are 0 0 x and v values, okay. And I call RK4. So, first I define n max and t max and calculate h from these, okay. So, I choose t 0 equals to 0, okay. So, that is why I calculate h is basically t max over n max, and this is my h values, okay, and h value, okay, and so I already quit this thing, that is why I quit, basically I already cleared all, okay. So, that means RK4 is already clear. So, you also you need to again compile this module, okay, before you calling. So, now we see this is a black, we can call this module, and this is the solutions, and we extract x 1, okay. So, this is basically as a functions of time, you can do similarly as before, okay. And then your values of x 1 is basically the last one, okay. So, this is an array, okay, and so array of array. So, because they contains both t value and x 1 value, right, but we want only x 1 value at the end, okay. So, at t equals to 5. So, basically end element, okay, end of yeah. So, at the last element in the array, okay. So, yeah. So, you see, so this is exactly the same one, okay. So, 2.65, 2.65, okay. 2465, yeah. So, 89.2465, okay. So, you can also solve this in an analytical way. So, so I quit this thing. Okay. Now, I solve this using D solve. Okay. And this is my equation, second order equations. Okay. So, I put these equations x double prime t equal plus x t equals to t cube, okay, and these are the initial conditions, okay, x 0 0 and x prime 0 0, okay, and I solve x t as a functions of t. So, since I call D solve, okay, so this is basically analytical solutions, okay, not numerical solving. Okay. So, that is why they return the form of x t, okay. But if you call ND solve, they return actually interpolating functions. Okay. So, you numerically solve and at every time stamp. Okay. So, they basically create a grid and calculate every values of t and x t, and if you want to extract any intermediate values of t, they just interpolate. So, that is basically numerical solver actually do, but if you call D solve, they actually return analytical solutions. Okay. So, once you solve this, basically this is analytical form of these solutions. Now, we extract the values, the numerical values of this at t equals to 5, okay, from this. So, you will see the exact is basically again same, okay, basically up to 4 decimal place. Okay. So, this is same. Okay. So, you see that how RK4, okay, gives you the accurate result. So, the close to exact one. So, up to 4 decimal place. Right. So, you can solve any other thing, because in the assignment you see just there is a problem that is basically t to the power 4. Okay, that driven force is proportional to the power 4. So, you just put t to the power 4 and solve this. Okay, the same way. So, the various way you can solve, but so check that in which methods actually they ask for to solve. Okay. So, now I am going to solve another example, okay, another problem. So, this is basically a projectile motion. Okay. So, we solve the non-dimensional equation d 2 x dt 2 right equals to minus 1 over x square with x 0 equals to 1. Okay. And initial velocity is equals to 1.5 times the escape velocity, right. So, this is projectile motion problem. Okay. And again this is a non-dimensional equation. So, this is dimensionless equations. Okay. All the variables are dimensionless. So, x is the dimensionless displacement, t is the dimensionless time, okay, right. So, yeah. So, first we calculate the escape velocity, because your initial velocity is equal to 1.5 times the escape velocity, right. So, how to calculate the escape velocity? So, escape velocity is basically the velocity at energy equals to 0, right. So, you calculate the energy. So, 1 over 2 mv square. So, this is basically 1. So, dimensionless. So, it is v square minus 1 over x, the derivative of this, right. So, this is your force, and then basically you calculate the potential. So, basically you integrate, right. So, yeah, and so this is basically 1 over x, and from this you calculate the escape velocity. So, this is basically equals to 0 at e equals to 0, and at x equals to 1. So, because you see at t equals to 0, x equals to 1. So, your v is basically root 2, right. So, this is the escape velocity is basically root 2, okay, and your initial velocity is 1.5 times root 2. So, again we basically define two functions here, f1 and f2. Okay. You can also use the matrix form to solve these equations. Okay. But here I do this explicitly. Okay, so I define two functions here. So the first one, basically we can split this equation into two first order equations. So the first one is f1. So this is x2. Okay, and the second one is basically minus 1 over x square. Okay, so this is x1 and x2 is basically v. Okay, so yeah, I have to calculate the displacement at t max 2, sorry, at t equals to 2 and with n max equals to 300 using RK4 method, right. So for this you just call yeah, so first we assign and then you assign all the variables and then calculate age first. Okay, so from this, once you calculate age, then you assign the initial values to this variable. So initial value is t is basically t naught. Okay, then I run this t from initial to update. Okay, in a step of age. Okay. So that's why t equals to t naught, and then x1 is basically 1, right. So this is given at t equals to 0, and initial velocity x2 is basically 1.5 times square root of 2, right. Because in my problem is 1.5 times escape velocity, right. So and I perform the same loop again. So this is the fourth step. Okay, so I update things, and at the end I calculate the weighted average of this. Okay, since everywhere I use age, so that's why I am not using age here. Okay. So I hope it's clear, and similarly for x2. Okay, you calculate and then update the t with t equals to t plus age, and then you calculate again, we perform the loop. Okay, n max times. Okay. At the end your x1 value actually the values of displacement, okay, at t max, and x2 is return the values of displacement at t max. Okay. Sorry, values of the velocities at t max. Okay. So once you do that, so your x at t equals to 2 is basically x1. Okay, so this is 4.63998. Okay. So you can also solve this using this. So you can just yeah. So you can basically call this RK4 and define a functions in the matrix form. So, okay. So this is the exercise. Okay, so you can do. Okay. So this is a good exercise to play with. So solve the same problem. Okay, using this RK4 module. Okay. So before you use RK4 module, okay, you first compile this, because once you clear all, okay, that means all the variables modules are clear. Okay. So you can no longer call this thing because they are not defined. Okay. So you just clear these things. So make sure before you using anything, you have to clear. You have to call this. Okay. I mean compile this before you call it. Okay. Okay, and the last one I use. Okay, so I use RK2 method, okay, to solve the van der Pol oscillator. Okay, or also I can use RK4. Okay, both RK2 and RK4 methods. Okay, to solve van der Pol oscillators. Okay. So this is very interesting problems in the mechanics. Okay, it's a nonlinear dynamics problem. Okay. So let's first see, is anywhere I define RK2. Yeah, so first I compile the RK2 and RK4. Yeah, so this is RK4. Yeah, so I compile these two modules, RK2 and RK4. Now I call this here. Yeah, so this van der Pol oscillators, what the physics is basically behind this, that not all systems are returned to equilibrium, right? So there are so one of the example is the van der Pol oscillator. So this is a nonlinear dynamics. Okay. And the equations it becomes this. So d2x dt2 is minus mu times 1 over x 1 minus x square and dx dt plus x equals to 0, right. So, similarly as before, so these equations can be written as a set of first order equations, okay, coupled equations, and v is basically dx dt and dv dt is basically this mu times 1 minus x square v and then minus x, right. So, once you define, so how many variables are there? Mu, right. So, only one variables, right, and the parameter, right. Variables are x and t, but the parameter are mu, right. So, once you define the values of parameters mu, so this is 1.0 and yeah, so we define the functions into a matrix form. So, this is basically x comma v and then so the first one is v and the second one is basically mu times 1 minus x square v times minus x, right. So, and your initial conditions is basically I choose 0.10, right, okay, and I choose a is equals to 0.1 and I solve using RK2 methods. So, and my phase data is basically the second one. So, you see, so RK2 all and 2, right. So, this is my phase data. So, this is basically x, okay, x comma v, right. So, this is my data, okay, x comma v, right. Because once you call 2, so this is an array of first one time and the second one is basically an array, right. So, that phase data is basically written an array, right. So, you just check. So, this is an array, right, 0.10 array of array, right, and the contents x comma v, right. And now we plot this, okay, phase data, okay, and these are the level you know familiar with this already. So, if you plot, so the plot looks like this. So, you start from 0.1 and then you say at some point they actually reach to the boundary closed line, okay, closed contour, okay. So, initially they changes, but at some after some times they reach to a proper cycle, okay. So, this is called the limit cycle, okay. What is this? I come to this point. So, if you also plot a streamline plot, okay. So, you plot v and so this is your v and the basically vector form, okay. So, I plot v and this is my j axis. So, this is mu times 1 minus x square. So, mu times 1 minus x square times v minus x, and I plot x minus 3 to 3 and y v minus 3 to 3, okay. And so, this is my field, I show this field, okay. So, you see, so I field and this is my solution, so phase data. So, you see, so how they basically lead to after some times into one cycle, okay. So, now if you start, so this is a limit cycle, okay, right. So, a closed isolated trajectory in phase space, okay. It is a closed isolated trajectory contour in a phase space, okay. And it is self sustained periodic motions and this does not depends on initial conditions, right. So, basically if you start with the different initial conditions, I will discuss this more on this, but if you start with let us say 0.1, sorry, let us say I start with 0.2, okay. So, again if you just solve this, sorry, I have to solve again. Yeah, so if you see, if you start with 0.2, they actually again reach to same limit cycle, okay. So, but we start with the different points, but at the end you are basically reaching at the same point, so same cycle, okay. So, it's trajectory, right. So, it's a closed isolated trajectory, so this is a limit cycle, okay. And you can also solve using ND solve. So, so this is basically your yeah, van der Pol oscillator. So, I call VDP, okay, and this is my solutions, okay. The first is x prime t equals to Vt and the V prime t is the coupled equations. So, I solve this, okay. So, this is basically ND solve value. So, I just extract value of these solutions, okay. So, if you call ND solve, this is basically gives you a interpolating functions, but if you call ND solve value, that actually gives you a value, okay, at the different values of time, okay. So, t 0 to 40, okay. And your initial conditions, so I choose different initial conditions. So, set of initial conditions. So, first one is the 0.10 and the second one is 3 comma 0 and the third one is minus 2 comma 1, right. So, I choose 3 initial conditions, okay. And for this I construct a table. So, my solutions contents for basically as a grid of this. Okay, maybe I quit these things because somehow I assign the values of So, basically these two, I think somehow we assign the values of t. Okay, so I just quit this. Okay, so quit all or the clear all. Okay, you can also do works. So now I assign VDP and solve this. Okay, so basically I have to put the mu values and and other things are fine. So and now if you plot this, okay, so this I plot the parametric plots, okay, and I evaluate those, and if you see, so your red one I start from 0.1 with a V0, and the blue one I start from 3.0 initial value and with V equals to 0. So, on the 0th line, okay, and the third one I start some different points, okay, at x equals to minus 2 and at V 0 is 1. See, all the curves are basically converge to a isolated trajectories, okay, the same closed trajectory, right. So, this is the limit cycle. So, they do not depends on your on initial positions, okay, or velocity, right. So, wherever we start with, so they reach after some times into a closed isolated trajectory, right. So, this is called the limit cycle. So, you can also manipulate this thing. So, we just to basically solve these equations for different values of initial conditions, okay. So, here I choose again the different initial conditions. So, you see 0.1, 0.1, 2.5, 2.5, minus 2.5, 0.5, okay. And here I manipulate the values of mu. Okay. So, I fix 3 initial conditions, okay, but I vary manipulate mu, okay. So, 0.1 to 4.0. Okay. So, you see, so there is a slider for mu, okay. So, this is for mu equals to 1.0 because I fixed, so this is my, okay. So, the return the plot for 1.0, but we have slider, okay, 0.1 to 4.0, okay. So, you can change this, okay. So, if you change this, you see how it's actually changes. For large mu, okay, ultimately, right. So, whatever your initial condition is, so they reach after some time into one cycle. But for small mu, okay, okay. So, you can see it changes, right. The situation it changes, right. Down here, so in this case they are not actually converging to a one limit cycle, right, for small mu, but at large mu we see. So, there is something happens. So, if you fix this 1.38, so you see your blue line you start from here and your red start from here and black start from here, but at the end they are converged into this closed contour. Okay, you can also calculate at mu equals to 0. So, what is at mu equals to 0? So, if you plot at mu equals to 0, let us say this 0 to this, and if you plot at mu equals to 0. So, you see all the things are different, okay. So, the blue line contour here, okay, and black one is there, and this is the values of 0, and the blue one is there. So, they are different contours. Okay. So, at mu equals to 0, so this is a pure harmonic oscillator, there is a no limit cycle, right. So, there is a no common cycle, okay, right, for mu equals to 0. But for different values of mu, okay, so there is a limit cycle. Okay. So, that is clearly visible in the streamline plot as well. So, if you see the vector arrow, okay, so you see after some point this will converts into this limit cycle. Okay, and I hope it's clear. So, if you have any questions, you can ask in the forum, or you can also drop me an email. Okay, so that's all for today. Okay, we will meet next Tuesday at the same time, and in the next class I will discuss Monte Carlo method. Okay, so yeah, I mean, I think I will stop here. Thank you. Bye bye.